Okay, let's dive right into this explainer. Today, we're looking at one of the absolutely most fascinating stories in modern tech, the story of ARM. We're going to demystify exactly how a small, scrappy team took on the massive silicon giants of the 1980s and ended up building an architecture that, well, literally powers our modern world.
Just take a look at this number on the screen. 350 billion. I mean, that is just a staggering amount. That's how many ARM-based chips have shipped globally. We're talking about silicon that runs everything from the tiniest embedded sensors in your smart thermostat all the way up to Fugaku, which was just recently the world's fastest supercomputer. It's a scale that's honestly kind of hard to wrap your head around.
So, here is our agenda for today. 1. The Acorn origin story. 2. Designing the first ARM. 3. The 3 profiles of ARM. 4. Cortex-A for applications. 5. Cortex-R for real-time. And 6. Cortex-M for microcontrollers.
Section 1. The Acorn origin story. A small UK team takes on the giants.
Our story kicks off in the late 1970s with Acorn Computers. They had this massively ambitious goal, a government initiative actually, to put a computer in literally every UK classroom. Now, looking at this timeline, 1983 is when things get really exciting, because that's when the official ARM project started. This is where we meet the true heroes of our story, Professor Steve Ferber and Sophie Wilson. These were the brilliant minds tasked with designing the very first ARM processor, the ARM1, specifically to run programs efficiently on those Acorn computers. And as you can see, by 1990, the project was spun off entirely.
Section 2. Designing the first ARM. Elegance and simplicity over brute force. So, heavily inspired by some Berkeley reports on reduced instruction set computers, RISC, the Acorn team had this radical belief. They believed a simpler chip design could massively outperform the complex 32-bit designs that were totally dominating the market at the time. And the contrast here is just amazing. On one hand, you had Acorn's tiny team, where Sophie Wilson literally wrote the entire instruction set simulation in BBC Basic on a standard BBC Micro. On the other hand, the Acorn team had just visited a giant design firm working on a modern 32-bit CPU. That firm had this massive team, they were already on revision H of their design, and it was still crawling with bugs. The Acorn folks just looked at that absolute mess and confidently decided, you know what, we can do this much better ourselves. And that bold decision? It ultimately changed computing history forever. In November 1990, 12 of those architecture designers spun off from Acorn. They formed a joint venture with Apple Computer, yes, that Apple, and VLSI Technology, creating a brand new company called Advanced RISC Machines Limited. And where did they set up shop to revolutionize the computing landscape? In an old turkey barn in Cambridgeshire. I mean, you really can't make this stuff up.
All of this leads us to a truly fascinating question, right? How exactly does a single processor concept designed by a dozen people in a literal turkey barn back in the 1980s end up powering both our incredibly complex modern flagship smartphones and our simplest smart thermostats today?
Section 3. 3 profiles of ARM. The rule of 3, A, R, and M. The big secret to ARM's absolute ubiquity isn't some magical one-size-fits-all chip. Not at all. It's actually this map right here. ARM smartly tailored their foundational architecture into 3 highly efficient, highly specialized profiles. ARM Cortex is the brand name for their processor designs, and it perfectly splits into A, R, and M. Cortex-A is for application. Think your heavy-duty OS devices like smartphones and laptops. Cortex-R is for real-time, which is essential for things like networking and embedded control. And Cortex-M is for microcontroller, the tiny, super low-power brains inside IoT devices and sensors. Together, they literally spell ARM. ARM. Pretty clever, right? Now, what's really interesting about this slide is how you can see the architecture physically building upward, layer by layer, from the older ARM v5 all the way to the modern v8A standard. Over the years, they didn't just rebuild from scratch. They steadily added advanced blocks, things like Trust Zone, which isolates and secures sensitive data right at the hardware level, or advanced SIMD for processing multiple data points simultaneously. This layered, iterative approach completely transformed what these chips could actually handle.
Section 4. Cortex-A for applications, the heavy lifters of the ARM family. So when you need serious high-performance and complex computing capabilities, this is exactly where you turn. The absolute defining feature of the Cortex-A is right here, the MMU, or Memory Management Unit. This is essential hardware that handles virtual memory. But why does that actually matter for us? Well, because without an MMU, you simply cannot run a full-fledged complex operating system. It's the exact reason the Cortex-A series is fully capable of running massive environments like Linux, macOS, or Windows seamlessly.
And to get that peak computing performance, Cortex-A processors utilize some seriously complex features, like 15-plus stage out-of-order pipelines. Now, doing things out of order and having those deep pipelines definitely requires a lot more power, but the trade-off is just incredible speed. That's exactly why Cortex-A is the brain behind all of our premium flagship devices.
Section 5. Cortex-R for real-time, when precision and timing are everything.
Now we hit the middle ground of the ARM family, which is built for entirely different priorities than the A series. You're going to find Cortex-R processors hidden away in places like networking equipment, automotive braking systems, and deep embedded control setups. These kinds of devices, they don't need a heavy desktop operating system, but what they do need is strict, unyielding reliability. I mean, think about your car's brakes. They have to respond to incoming data absolutely perfectly and instantaneously, every single time without fail.
Section 6. Cortex-M4 from Microcontrollers. Small, low power, and bare metal.
Finally, we have Cortex-M, which totally disrupted the market by slowly replacing legacy 8-bit chips, bringing robust 32-bit math operations down to the absolute lowest end of computing. And unlike Cortex-A, Cortex-M operates entirely without an MMU, usually running what we call bare metal, or maybe just with a tiny real-time operating system. Down at the hardware level, it includes some highly specialized features for this kind of environment, but the real star of the show here is the TCM, tightly coupled memory. TCM provides zero-weight state memory. It's basically as incredibly fast as a processor cache, but it's fully addressable. And that is absolutely vital for executing speed-critical code without any unpredictable delays.
Zooming back out to the macro level for a second, this extreme energy efficiency is honestly what makes our modern, smart life possible. Cortex-M is the exact architecture that enables always-on AI voice activation running in the background, massive smart home ecosystems, and those tiny wearable IoT sensors that can just run for months and months on a single tiny coin cell battery.
Section 7. The most pervasive computing platform, from the BBC Micro to global ubiquity.
And this brilliantly illustrates the whole journey. We started with the simple, elegant design of the ARM1. But instead of just bloating that single design over the decades, they smartly splintered it into this perfect trio of profiles, A, R, and M. That move allowed them to conquer literally every single corner of the tech landscape. The final result of that strategy is perfectly captured by this quote right from our sources. ARM is the most pervasive computing platform worldwide today, with the technology touching 100% of the global population. 100%. I mean, that is an absolutely staggering, unprecedented scale of success for a company that started its journey with just 12 people in a turkey barn.
So, I'm going to leave you with this thought. With ARM chips essentially in 100% of our hands right now, silently running in the background of our daily lives, what unexpected devices is architecture going to transform next? Thank you so much for joining me for this explainer, and definitely keep an eye out for ARM the next time you turn on, well, pretty much any device in your home.